that is on. Welcome. Today we get to play a bit with sound and music, some of the most universal and multidisciplinary applications of really basic physics and really basic mathematics. We have a Learning Catalytics question going, so if you can answer that while I am speaking, and we'll give people another minute to come in. So if you've already answered the Learning Catalytics question, turn to your neighbor and talk about, you've probably all experienced that sometimes notes sound good together and sometimes they don't. And talk to your neighbor about when that happens. Why is that? Why do you think that is? You know, if you're not sitting near anybody, feel free to move. Go ahead. We'll give people a few more seconds to filter in and respond to the Learning Catalytics question. So last time on Monday, Jason played for you a range of frequencies, right? Pure tones, pure frequencies. You discussed how sound is how different notes correspond to different frequencies. In real life, of course, sounds are made up of a bunch of different frequencies. And here we have an oscilloscope showing us the frequencies of sounds that go into the microphone. So if I talk into this, various frequencies are being excited there. And most sounds are a bunch of frequencies. They're not just one frequency, right? However, sometimes we can't, if we produce a bunch of frequencies, only one will stick. We'll see if this works at all. Can you guys hear that? Like a really low note, which I could double actually by doing this. And the frequencies that are selected, if you will, by this pipe, are the frequencies that fit. What do I mean? The notes that fit. Literally the wavelengths that fit. And you may remember from the pre-class, these standing waves. This idea that we can fit a certain number of wavelengths on a string or in a pipe. In a pipe it's open, well, you could think of that as the pressure. And these are the different, can we fit both of these? Ooh, maybe we can. Almost. These are the different harmonics in this tube. And so we're gonna try to excite these by putting air through this tube. Can you hear that? Yeah, so that's one note. And as I do this faster, we can pick out certain other notes. And those of you with some musical instrument experience may realize these are notes in a major chord. So that's the fifth above the note I was doing before. The octave. And I can almost get to the third above that. So there's something special about all these various harmonics that fit within this tube. This tube can do all of them. And we also have our university organist here. John, was it? John. And since we're in this space, why not make use of this fabulous organ we have here? So if we want to play just one note, let's just play one note on the organ.
I'm going to use the softest stops because I can get the whole range of stops which provide those harmonics.
Okay, sure. So we got one note.
That's the tonic or the fundamental. First harmonic.
Oh, is that not on?
Or it's not reacting very well. Maybe too quiet.
So you're hearing these various notes being added, yet it also sounds like a more enhanced version of that one note.
That's actually 6 pipes playing at once. Each one playing.
Here, you want to talk into this?
It's 6 pipes playing at once, the fundamental tone and the 5 harmonics above it, I'll play them again. I'll play them individually.
He'll play them individually.
Or together. So it sounds like one voice.
Were we able to see the different notes on here? Yeah, you guys could see that. You can see it going up as I go higher. Cool. I did forget to reference that as I was doing this. We have a couple singers with us today over for music, Kai and Cynthia. So when we're talking or singing a note, our vocal cords produce, again, just like with the pipe, there's a whole bunch of frequencies being produced. And we can select out which frequencies are louder or softer by the shape of our throats and mouths, right? We're actually creating vowels by modulating what overtones come out. So let's start with just simple vowels. Would you be up for that? And hopefully this will pick up. What did you notice about the different vowels? What changed? People typing? I guess I could. Do you want to see it again? Okay, let's see it again. And what we want to look at is what do you notice? So there's going to be, maybe start with ooh, so we get a really strong fundamental. So let's find that fundamental. So you see how that's the note that you're hearing as that note. Ooh. And then what happens is they change the vowels. Go ahead. Yeah. Mm-hmm. Thank you. Mm-hmm. Mm-hmm. So as you switch from different vowels, you're changing which overtones get excited, in the voice. And I'm really excited to have them here because they can actually do overtone singing. So you can get these really, you can excite some of these harmonics really loudly and get these whistle tones, which they will demonstrate.
Okay, so the fundamental on the singing
Here,
sound.
talk into this if you want.
Oh, is ooh, ooh. That's the bass note that I'll be singing, and then everything else that you might hear is just like because of mouth. Physics.
Do you hear these little whistle tunes?
And then, yeah, third and then the fifth. Yeah?
Okay.
That's my fundamental pitch.
That's her fundamental pitch. Cool.
I'll do higher.
Sure.
Ooh, that's my fundamental.
Cool. And lastly, as a final piece, since you'll be doing beats today, I thought we'd ask them if they could sing beats. So this is when you get two and go in and out. So when you have, again, if you're combining notes that don't sound so great together, right, that are not consonant, that clash, why do they clash?
Here's the fundamental pitch that I'm going to sing. You guys are going to join me on a variation of that.
Yeah.
Yep. It actually feels like a physical sensation. I can feel the beats. Yeah.
You can physically feel the beats.
Sure.
Let's have a round of applause for our singers.
Well, thanks again, Carolyn, for all of that. Okay, so we're back to this stuff. So, once again, we're in our last week. Tomorrow we're back from 11 to 12. I'm sort of finishing up this chapter 14, and we'll be talking a little bit about some tips for the final exam, which is a week from today, I guess, on Wednesday morning. And then also we will be participating in the exam jam on Friday if you want to turn out for that. But all of this stuff, once again, sound wave intensity, the decibel system, wave interference. So this is constructive, destructive interference. I think we see right here at this point of destructive interference when we have two waves oscillating out of phase or in phase. At different positions, you'll have destructive or constructive interference. We'll talk a little bit about that today. Beats, we talked about that a little bit. But all of this stuff is sort of this light touch. Unlike, I guess, chapters 1 through 13, where we went pretty in depth into all these subjects, I think chapter 14 at the end, we're kind of introducing these concepts. I'd like you to be able to apply simple equations, like the equation for beats. We'll give some examples of that, but it's not going to the prepare you for second year physics kind of level with this stuff. So, do you want to talk about wave intensity? Intensity of a wave is like kind of how loud it is or how strong it is. It is equal to the average power it carries per unit area. And the idea is, it's pretty simple. If you are, I guess, far away from a sound, it sounds quieter. Or, if you hold a light bulb up to your eye, it looks really bright, but if you put it on the other side of a lake and look at it, it looks really faint. The reason for that is whatever energy which is coming out into the waves gets spread out over more and more space as you get further and further away from a source. And we call it like a point source because it's at some point in space, in 3D space, and it's radiating out into all three dimensions. So at some distance r1, the intensity is I1. At a distance r2, further away, the intensity gets less, even though you actually have the same amount of average power over both spheres, since it's power per area. As the area gets greater, then the intensity decreases. So that's that concept. Another way of looking at it is that, I guess, if you have a little tiny hole in the window and there's sunlight coming in, you'll get a little bit of light in the room. But if you open up the curtains and increase the area of the window, more, I guess, light will come in. So somehow, and that's sort of like power is the intensity times the area. So there's some intensity of sunlight falling on your window or on your house, and the bigger the area of the window, the more of that light can come into your house. So more power there. So this is why you use the area. So here's a wave coming along. It's going from maybe right to left there, and it carries with it some power, some amount of energy per second in these waves. And then if it goes through this area, the amount of power that goes through that area is P, and the intensity is P divided by the area, power to area ratio. An example of my laser pointer, which I put over there, if you had a laser pointer that emits 1 milliwatt of light, and the beam diameter is 1 millimeter, you can calculate the intensity of that beam. Which I did here. So it sort of looks like this. There's the beam. It has some area, which is lowercase a, is going to be pi r squared. And r is going to be the diameter divided by 2. So r is going to be 10 to the minus 3 meters divided by 2. And so the intensity is just the power in that beam divided by the area. Power of the beam is 10 to the minus 3 watts. That's what that milliwatt means. And then divided by pi times 10 to the minus 3 over 2, all squared. And I got 1273 watts per meter squared. That's the intensity of the beam. That was pretty bright. And then if you want to, so that's a beam that's not spreading out spherically, like it's not like a light bulb. So if you turn on a light bulb, the light goes everywhere pretty evenly. But a laser, all of that energy is in this little beam. So the equation for the light bulb is I is the P divided by 4 pi r squared. So if a source of spherical waves radiates uniformly in all directions, which a laser definitely does not, then the power at some distance r is spread uniformly over the surface of a sphere of radius r. Okay, so this equation is for whenever you have a source that we call it isotropic, meaning it radiates the same intensity in all directions. So as another example, I will say, from the previous example, a laser pointer has an intensity of 1273 watts per meter squared. How far from a 100-watt light bulb should your eye be in order to have the same intensity as shining this green laser directly into your eye? Neither of which I recommend. It's not good to shine a laser into your eye, but just sort of a rough example there. So I'm going to assume, I guess, the bulb has 100% efficiency, because I haven't been told the efficiency, which it definitely would not have. Efficiency. So all 100 watts goes into the light. In reality, a real light bulb, incandescent bulb, has about 5% efficiency, so 95% of that 100 watts, 95 of those watts goes into heat, creating heat, and only 5% makes it into light, but let's just assume for now it's 100%. So then what you've got is I, the intensity at whatever distance you're at, is equal to the power divided by 4 pi r squared. And what we're going to do is we're going to set I is equal to 1273 watts per meter squared, and P is equal to 100 watts, and solve for R. So you're going to get something like R is equal to R squared is P divided by 4 pi I think. So R is equal to the square root of this power, 100 watts, divided by 4 times pi times the intensity you want, 1273 watts per meter squared. And you end up with, I got 0.079. And the units are, well, they're just meters because of the distance. So if you hold your eye about 8 centimeters from a light bulb and look straight at the light bulb, you're getting about the same amount of energy, power going into your eye as you would if you took that laser and shone it directly into your eye. Again, please don't try any of this at home. It's not good, and you can damage your retina by looking that close at a light bulb or shining a laser into your eye or looking up at the sun. All of these things can burn little holes in your retina and cause permanent eye damage, so don't do it. And good rule of thumb is if it hurts, stop doing it. Yeah. Another thing that kids know and physics proves is also correct. Okay. Okay, so this is this crazy decibel system. So, intensity. Thing to remember here is intensity is the real physical thing. Watts, which is joules per second per meter squared. Everything's in SI units, everything's very physical. You're describing actual energy transfer. So then there is this interesting fact that human beings can hear very quiet sounds, extremely quiet sounds, down to 10 to the minus 12 watts per meter squared. You can hear that. And we can also tolerate extremely loud sounds. So you can go to a rock concert and listen to a rock concert and have fun, even though you're up at the watts per meter squared of actual sound getting into your eardrum, and it doesn't damage your ear. So somehow your ear is able to deal with like a factor of 10 to the 12 in range of intensity, and still you can still deal with it. So somehow we think that our ear is some kind of a logarithmic detector. What we respond to is not so much, I guess, how much intensity is added to a sound, but how much it's doubled or how much it's gone up by factors of 10. So what we do is, for our human convenience, we write down this crazy equation. Humans love it. Physicists don't like it much because there's a whole bunch of math, but basic idea is that this is a logarithm. So the definition of a logarithm is that 10 to the power of the log base 10 of x is equal to x. So when you raise 10 to the power of this log thing, you get that log thing. So example, if you want to convert, this is to convert intensity to your sound level in decibels beta. If you have beta and you want to solve for I, let's do solve for intensity. It looks like this. You take beta divided by 10 is equal to log base 10 of I over I sub 0, where I sub 0 is the threshold of hearing, some small sound. And then you raise 10 to the power of both sides. So you say 10 to the power of beta over 10 is equal to 10 to the power of log base 10 of I over I sub 0. But due to the definition of logarithm, this just equals I over I sub 0. So I is equal to I sub 0 times 10 to the power of your beta divided by 10. So if you had something that was, if it was 0 decibels, for example, if beta was 0, then 10 to the power of 0 is 1, and so your intensity is I sub 0, the threshold of hearing. So the threshold of hearing is what we define as being 0 decibels. Here's a chart. So start at the bottom of the chart. Threshold of hearing, 0 decibels, that corresponds to 10 to the minus 12 watts per meter squared. And then, since it's logarithmic, every time you go up by a step of plus 10 decibels, then you go up by a factor of timesing by 10 watts per meter squared. Okay, so 20 decibels is like a whisper, and that's like an average whisper, not the faintest whisper you can hear. That's 10 to the minus 10 decibels. Then quiet radio in your home, 40 decibels, that's about 10 to the minus 8. Busy street traffic, 70 decibels. I've turned on my, I have a decibel meter on my phone, but if I turn it on in like that Fresh restaurant on Bloor and Spadina, it's always about 70, 75 decibels in there. It's a really loud restaurant. That's 10 to the minus 5 watts per meter squared incident on my ears. Okay, with train going by, subway going overhead, 90 decibels. The threshold of pain is 120 decibels. That's when it starts getting really, really painful. And you close your ears and you go like this, ah! Well, that's 1 watt per meter squared. And of course, if there's a jet plane going by really close to you at 30 meters away, that's well beyond a threshold of pain, and you can really start damaging your eardrum with that kind of sound level. Okay. So, We're going to do some learning catalytics on this because I do expect you to know the decibel system. It's one of the light touch things. Not that hard, it's a logarithm. And this is sort of conceptual. Have we delivered it? No? Maybe I have to stop the, let's stop the first one and deliver this one. Yeah, there we go. Okay, so now you should see it. A sound level of 10 decibels has 10 times more intensity than a sound level of 0 decibels. So a sound level of 20 decibels has blank times more intensity than a sound level of 0 decibels. Fill in that blank. Tell your neighbor. I'll give you a minute. Yeah, so people mostly figured this out. The idea is that every additive step of plus 10 decibels in the sound level, sound intensity level as it's called, corresponds to a multiplicative step, factor, I guess, step of timesing by 10 in intensity, the real physical thing. Okay, so sound intensity level, this human-created logarithmic scale, which is used by city ordinances and things, so the police can measure your decibel level and tell you whether or not your party's closed down, versus the physicist's real measurement of intensity, which is watts per meter squared. Okay, let's do another one. Sending this to your phone right now. So, let's say you have your iPod set to 50 decibels, which usually says 5 if you do have a knob on your volume, and you turn it up to 8, so 80 decibels. So by what factor has the sound intensity, physical intensity, increased on your eardrum? Give you a minute to think about that. All right. Yeah, so 1,000, so that was good. And again, idea is 80 minus 50 is 30 decibels. 30 divided by 10 means you've done 3 steps, I guess, of these 10, and so 10 to the power 3, 1,000 times the intensity. And yeah, I do have a goal, maybe next Learning Catalytics question, I really want to play like one of those big pipes on the organ. I've been looking at those things, but never gotten one going. But let's continue a little bit with principle of superposition. I do want to motor through these slides a little bit. Basic idea is that if 2 waves combine at a given point, then their disturbances combine. So remember when you had a wave going along in one direction, there's actually 3 dimensions going on. There's the x direction, which is the way it's going. There's time. And there's the disturbance, which we called y if it was a wave on a string. So if you have 2 waves and they're passing by the same position x at the same time t, then you just add their 2 disturbances. It's a pretty simple concept. This is called interference. The principle of superposition leads to the concept of wave interference. The pattern resulting from the superposition of 2 waves is called interference. Interference can be either constructive, meaning that they're both the same sign, y1 and y2 are the same sign, so when you combine them, you get more amplitude. Or destructive, meaning y1 and y2 have opposite signs, and then when you combine them, you get less amplitude. So example, this is a point of detection where you have 2 speakers set up playing the exact same note with the exact same intensity. If you displace them by just the right amount, half a wavelength, then you can actually have perfect destructive interference and create silence. And there are noise canceling headphones that you can buy for air travel where You put on the headphones, they have a microphone which picks up whatever the sound is, the ambient sound in your environment, and then it produces this same sound, exact same sound, but flipped by a phase of 180 degrees, or sort of flipped upside down. So it's like an anti-sound, and plays that sound into your ear. And then when the two sounds combine, the ambient sounds and the anti-sounds being created by the speaker in your headphones, they cancel out and you get silence. Sort of works. It's a nice concept, but the microphone has to be very, very sensitive and to all the different frequencies, has to be able to pick up the frequencies, and the electronics has to be able to flip it in a very short amount of time. So it works for low sounds, it doesn't work all that well for high frequency sounds. I'll talk about beats a little bit. The singers tried to make beats, but I found it a little hard to hear it. But the basic idea is that the intensity of the sound goes up and down as time goes on. It occurs when two waves of similar but not equal frequencies are superposed. And so you can compare the frequencies, and there's some math of it. So I'll do it in a little bit. We have two tuning forks here. These forks are set to, they're both 256 hertz, but so it sounds like this if you do one of them. 256 hertz. So I think that's I don't know what that is, but it's a C, I think. Maybe it's middle C. Anyway, one of them is 256 hertz and one's a little bit out of tune. I think this was the one that's in tune. This one's a little out of tune. So do you hear it going up, down, up, down? It gets loud, quiet. So what's happening is these two waves, both at almost exactly 256 hertz, are interfering. One must be either at, sounds like about 1 hertz beats.
Whack it really hard.
Really hard? You can hear it now, right? It sounds like about 1 hertz is the beats, about every second, maybe half a second, something like that. So if it's half a second beats frequency, then that means that the difference between these two frequencies is half a hertz. So it must be one of them's 256, and this one with the weights on it must be either 256.5 or 255.5, so that the difference between them is about half a hertz. I'll show you how that math works. So an application of beats is they use it for piano tuning. You can listen to the disappearance of beats as you match two frequencies. If the two frequencies are equal, then the beat frequency goes down to 0, and for the infinite period, I guess. So, and it looks like this. I'll show you the equation the only useful equation that you need on your aid sheet, that it's hard to sometimes find, is the frequency of the beats is equal to the absolute value of F1 minus F2. That was the one you sort of needed for this morning's pre-class quiz. That was right here. Okay. So let's just write that on the next sheet here. I think that's the main takeaway, is that F beat is equal to the absolute value of F1 minus F2. So example, the tension in each of two strings is adjusted so that both vibrate at exactly 666 hertz. The tension in one of the strings, let's call this string 2, I guess, is then increased slightly. As a result, the six beats per second are heard when both strings vibrate. So that means F beat is equal to 6 hertz, 6 beats per second. And so that means that 6 is equal to the absolute value of F1 minus F2. And so if F1 is equal to 666 hertz, then you have to solve this absolute value thing. There's two solutions. F2 is equal to either 660 hertz or 672 hertz. Both of those are a solution. So, and then you need another piece of information, which is that for a standing wave, I guess, with fixed length, then the frequency is proportional to the v of the wave. Okay, and the v of the wave in a string is equal to the tension in the string divided by the mass of the string. So basically, as v wave increases, it means the frequency increases. So since you increased the tension in the string, you must have gone to a higher frequency. So I think the answer then has to be 672. It rolls out to 660 because that's below. So that's what the answer I was looking for there. So first piece of information, beat frequency. That gives you two possibilities, and then you resolve it by saying, well, what happened? Did I turn upwards or downwards? So you can't tell just by counting beats whether you're a little above the note or a little below the note. You have to then test it. If you've ever tuned in an instrument, you kind of, using this idea, you may have done it. Yes? Yeah, well, because you've increased the tension. The F is the tension. So if you increase the tension, increase the speed of the wave. So let's go on to this great big standing waves thing. I have a giant rubber hose that I brought with me. And it's string, so I can have some tension. I can have low tension, whoop, or... Oh, you're going to hold it? Okay, good, yeah. So I'll just increase the tension and Kevin will be the other side. Okay, so right around there. So we can make a wave by hitting it. And this is what I was kind of imagining, is if you're dangling from the bottom of a rope, you hit it, you could send a signal to the other person. You send an upward pulse, send a downward pulse. And what we could do, there's always reflections, I could send an up and a down, whoop, and have it destructively interfere somewhere in the middle or something, but I think it flips, right? It seems to flip so that when it hits Kevin, it comes back inverted the other way. So maybe I need to send two positive pulses. Oh. We'll have to slow down that video on YouTube and see if we can get it. Anyway, so the other thing you can do is send a sine wave along. Whoop. Yeah, there you go. And then you start interfering both directions. So what I'm going to do is set up a fundamental standing wave. So this is when I send a frequency of a sine wave such that the wavelength of whatever wave I'm sending to Kevin is twice the distance from here to Kevin. So I get half a wave in the middle. That's called the fundamental frequency. When you pluck your guitar string, you get that particular frequency. It's the main one. If you increase the tension, hold on, then the same fundamental frequency now gets higher. But then I can also double the frequency and get the second harmonic. So this is the m equals 2 mode. And so when the side close to me goes up, the side close to Kevin goes down, and right in the center there, near the microphone, it's not moving at all. And that's called a node. Let's see if we can get three times the fundamental frequency. Oh no, that's wrong. That looks like about 4. I'm going to do 3. There we go. That's the third harmonic. So again, this is going to be 3 times the frequency of that original fundamental mode. And again, actually, we can spin it. I tried to get it about 4, so there. Thank you, Kevin. All right, so that's standing waves. It's caused basically by reflections going back and forth. Should I show the math? Yeah, I'm going to show the math. This is the basic math, which is saying that, okay, principle of superposition, you have 2 waves. And now what I have is a sine wave that's traveling to the left and another sine wave that's traveling to the right. And they're passing through each other. So you add these 2 cosines. One, if something's traveling to the right, it's cosine of kx minus omega t, and the other one is cosine of kx plus omega t if it's traveling to the left. So then you simplify by using a trig identity, and what you get is the product of 2 sine waves. Sine of kx multiplied by cosine of omega t. So what that means is that the amplitude depends on position, but every particle is just oscillating sine omega t. So you have simple harmonic motion where the amplitude now depends on position. And it depends on position like a sine wave. So here's a learning catalytics question for you. So send. Which is, so what this is showing is, I guess, like 3 snapshots overlaid or something like that onto the same thing. So at one instant it's this one, at another instant it's this one, at another instant it goes flat. Okay, so it's, I don't know if you can imagine what I'm trying to sketch there, but lots of flashes of a standing wave going by. So what is the wavelength? Is it 0.25 meters, 0.5, 1 meter, or 2 meters? Or is it true that standing waves don't have a wavelength? I want you to think about that for a minute. Answer is, okay, this is a bit tricky. I think the answer is actually 1 meter. And the idea here is that it's 3 different times. So maybe time 1 would be this one. Okay, and time 2 would be this one in the middle. And then time 3 would be this one. But in any case, the distance that it takes to repeat one time is actually 1 meter. You might have thought half a meter, which would have been a good guess, but it's actually twice the distance between adjacent nodes is your wavelength of a standing wave. And, okay, the next thing is just about, so that's, nodes and antinodes are spaced half a wavelength apart. So the next thing is that, this is sort of what Carolyn put up at the very beginning, is that on a string of length L with fixed endpoints, you force a node on the standing wave to be at both ends. So there's the fundamental modes where we started. This is your m equals 2. It's called the second harmonic. M is called the mode number. And here's m equals 3. Only oscillations with particular wavelengths are going to be allowed on this string. They have to have a node at either end. That's the, I guess, the constraint of the 2 boundaries. Kevin on one side, me on the other. We're holding it fixed. And so those have to be nodes, but you can have any integer number of nodes in the middle, which could be 0 for the fundamental mode. So what is the mode? And they call that m equals 1 is the fundamental, m equals 2 is that one, m equals 3 is this one. So this is another quick question. What mode is that? I'll kind of leave that up, but the other thing I'm going to do, I don't know if you can see those giant pipes above the screen, but there's a really big one, and if Lillian figured out, if I step on this, you hear that? I can make that lowest note, which I love. And then, are these other pipes? Oh. I don't know what note that is, but it's pretty low. It must be, oh, it's a little higher. I really probably should not be on this, because I'm not at all qualified. But what happens if you hit these things? They don't work. Okay. Anyway. Okay, so answer is, I'll just tell you, the mode number of this standing wave is going to be 5, and this is called an m equals 5, and all you do is you count the antinodes. So there's like one antinode, so count the antinodes. If there's one antinode in the middle, that's the m equals 1, the fundamental. If there's 1, 2, 3, 4, 5, then that's the fifth harmonic, as they call it. So I'll talk a little bit more about this and how it relates to music tomorrow. This is the list of things to do tomorrow. There's no pre-class video for tomorrow, because we're done. And there's no pre-class quiz. But there is a homework 11, which is for practice. It's not for marks, but it is stuff that's going to be covered on the final exam, so you might as well do it. We're not going to do the Doppler shift in this course. Tomorrow I'm going to finish up to the end of 14.7. Do a little course review maybe. And then Professor Wilson and I will be giving back-to-back exam jam lectures on Friday from 1 to 3 in Sid Smith. which you can check out. Otherwise, I'll see you tomorrow. Same time, same place.